Recording is rolling. It is Thursday, April 24th. A bunch of guys just hopped on Kahoot. There's a bunch of relativity questions. You guys know past few days we've been doing relativity. Got some relativity posters queued up, ready to go for Kahoot. Your guys' cogwheel and relativity puzzles. You guys remember 2 days ago, spent a lot of time in class solving Fizzo's cogwheel, and then spent a lot of time in class yesterday. You guys were solving these relativity puzzles. There's dilation questions, there's mass energy equivalence questions, some other conceptual questions. So a lot of students turned that in yesterday, turned in that paper. Guys, if you haven't turned that in yet, make sure you get it in before the end of the week. So tomorrow, because you guys know today is the last day of the grading period. And then you guys know all your teachers have to get their grades in by this weekend. You guys know that? And so whatever you have turned in by this weekend is going to show up on your interim report. So probably a good idea to check this class, all your other classes, make sure you're not missing anything. All right, now we will have about 15, 20 minutes at the end of class today, so I will roll a nuclear energy PowerPoint for you guys. All right, so you guys ready for Kahoot? Kahoot. Oh yeah, look at you guys, ready to go. It's Kahoot time. All right, see what you guys have learned the last few days. Special relativity. In contrast to an object with mass, no matter how fast the source of light is moving, light always has the same speed. Okay. Remember, this was in contrast to Newtonian relativity. If you're, say, on a moving platform and you throw a ball, how fast the ball is going? Well, it depends. Are you on the platform or are you standing on the not moving ground? You would get different answers. But if you measure the speed of the headlights of, say, a moving train or a moving rocket, everybody agrees on the speed of light, regardless of if you're on the rocket or on a stationary planet. And of course, that led into time dilations and the whole deal. All right, got points on the board. Einstein reasoned all motion is relative. A spaceship cannot measure its speed relative to empty space. A spaceship can only measure its speed relative to other objects. All of the above. What Einstein reasoned. No, it cannot be all of the above. Yeah, all those. So we say motion is relativity. Motion is relative to some other object, but not to empty space. That's not a thing. So, like, how fast is the Voyager spacecraft going right now? Well, you get an answer that relative to Earth, or relative to our sun. But that would be different relative to, say, a different solar system. Guys, is the universe expanding right now? The universe is expanding. Okay. There's something called the cosmological principle. This idea that there is no center of the universe, or sort of the center is kind of everywhere. You can pick any galaxy, and kind of all the other galaxies are headed away, right? There's an analogy I heard I think is pretty good too. If you blow up a balloon and you put a bunch of dots on the balloon, yeah, I'll draw this out for you guys. I draw dots. So help explain something called a cosmological principle. Ooh, I think I need a new pen. Because I suppose you blow up a balloon and you put a bunch of dots on this balloon, right, just covered in dots. Right, and you keep blowing up, so now it's like this big. Okay. And now, guys, are these dots spreading out? These dots are spreading out. Right. But is there a single dot you can point at and say, oh, that's the center of the surface of the balloon? Is that a thing? No, not really. Okay. So throw in an extra dimension and you get universal expansion. And there is no center of the universe. So when, starting from the Big Bang, all the galaxies are racing away from each other. There's no central point to the universe. Right? That's part of this process, this relativity process. I got Luciana, Hunter, good boy, Tommy Two-Tone, Alexander, Peyton. Spaceship moves away from a space station at half the speed of light. If a person on the space station flashes a light beacon, the people in the ship will see the light traveling toward them at a speed of what? Speed of light. Yeah, speed of light. Here, I'm going to draw this out. make for sure that you guys get this concept. Okay, so they got a planet here. Okay, and let's throw a station here. Station. Okay, and it's sending out electromagnetic waves, so sending out some signal. Here, I'll draw Earth twin. Here's Earth twin on the station. Okay, and flying by at half the speed of light is this rocket. Well, was marks, and here's rocket twin inside this rocket. This rocket's going so fast, it's going v equals half the speed of light. Okay. Hey guys, this tower right here, sending out EM signals. Are these waves traveling at the speed of light? Yeah, so these are traveling at speed of light, call it c. Okay. Now, if Earth twin here, I'll call this guy E for Earth twin, this guy R for rocket twin. If Earth twin breaks out a Fizeau cogwheel and measures the speed of these light waves, these EM waves, does he get exactly the speed of light? Yep. How about rocket twin? Suppose rocket twin breaks out a Fizeau cogwheel and measures the speed of these EM waves. Is it still the speed of light? Yeah, sure is. So they both agree to speed of light. Remember, the only thing to make that consistent is you have to have time dilations and the whole deal. We got Alexander, Peyton, Dallas Stars, Luciana, Tommy Two-Tone. Suppose you observe a spaceship whizzing past us at very high speed. Sounds like the picture I just drew. Compared to what the person in the spaceship sees, we see the spaceship clock as running what? Slow. Yeah, one winner. One winner. All right, let's check this out. Okay. So, here, since I got this picture up here, let's start with the picture. So, suppose Earth Twin has a clock. You guys see Earth Twin's clock right here? And Rocket Twin also has a clock. Let's draw a Rocket Twin clock right here. Okay. And they can, of course, see their own clocks. Right? Now, guys, if you're on Earth and you're looking at the Earth clock, do you see your clock ticking 1 second per second? Yeah, the time's normal. If you're inside the rocket going half the speed of light with Rocket Twin and you look at your own clock, do you still see 1 second per second? Guys, show hands. Who says yes? Who says Rocket Twin sees his own clock beating at 1 second per second? Yeah. Right. Now, here's the conundrum. Is if these two twins break out telescopes and they look at each other's clocks, now does the other guy's clock look like it's a mismatch? Yeah. So which way does the story go? If Earth Twin's looking at Rocket Twin's clock, it looks like it's ticking really what? Really fast or slow? Tick, tock, tick, tock. I think it's going really slow. Versus Rocket Twin looking back at Earth, is this clock going like that? No, but that might be like 99% the speed of light. You guys get it. Something relativistic speed. Right? Oh. How about this, guys, in the twin paradox? This is the twin paradox story, isn't it? The two twins started out both on Earth. They were the same age. Which twin? So Rocket Twin takes off in a rocket, flies around close to speed of light for a couple of years, comes back. Guys, which twin became really old and had a long gray beard? Was that Rocket Twin or Earth Twin? That was Earth Twin, because his clock was beating relatively faster. Okay? And then here's an equation to back all this up. So you move at a relativistic speed. So spaceship speed is some significant proportion of speed of light. That means this fraction is between 0 and 1. 1 and minus that, same story. Square root of that, same story. Guys, this Lorentz factor, you guys see this whole square root? At a relativistic speed, this is bounded somewhere between 0 and 1. Let's call it 0.5, just to throw a number at it. Okay. If Rocket Twin right here says, oh, like 1 year has passed, I've been flying around for 1 year, and you divide by 0.5, what does that give you? What's 1 divided by 0.5? 2. Yeah. So Earth Twin says, no, I think 2 years have passed, right, which is more time. There you go. So there's a few perspectives on the answer to that question. All right. You're moving on a high-speed spaceship relative to Earth. You would notice your pulse slowing down. Notice all your clocks are slowed down. Both the above, none of the above. You are Rocket Twin inside your own rocket. What do you notice about? Yeah, none of the above. Right? Remember, in your frame of reference, as Rocket Twin, you notice nothing strange in your own locality, in your own frame of reference. Okay? Now, talk to Earth Twin, it's a different story. I got Peyton, Luciana, Tommy Two-Tone, Alexander, Dallas Stars. According to special theory relativity, all laws of nature are the same in reference frames moving at constant speeds, reference frames that accelerate, reference frames that oscillate, inertial frame of reference. 2 of those are correct. Just pick one of the correct ones. Yeah, only for inertial frame of reference, which could either be at rest or constant velocity, which is physically is the same thing because motion is relative. All right. All right. Clocks on spaceship moving very fast appear to run slow when viewed from. Yeah, say Earth, inertial frame of reference, stationary observer. Okay, same idea. Right. As long as you don't hop on board the rocket. I got Peyton, Luciana, Dallas Stars, Tommy Two-Tone, Alexander. You're actually looking into the past. Ooh, guys, which one's technically correct? Technically correct. Maybe a little tricky answer to this one. What's technically correct? Okay, yeah, so I'm looking for both the above. No, guys, starlight it would definitely be true, right? Because doesn't it take several years for starlight to reach us because they're light years away, right? So, guys, all of those stars you see at night, it took several years for light to reach us. But really, anything you look at, if there's a physics book that's 2 feet from your face, did it take a tiny, tiny, tiny fraction of a second for light to reach you? Yeah, right. You guys remember that Minkowski space-time diagram? You guys see up there? So anything like any light that enters your eyes comes from the past, one way or another. When you approach a light source, the wavelength of light appears. Shorter. Right. When either you're approaching light source or if the source of light is approaching you, the answer would be the same. Ooh, guys, what's the name of that effect? Starts with a D. Doppler. You guys remember Doppler? I have my posters out for Doppler, so let's do that. Right. Now here's the old version of Doppler. You guys remember for sound specifically? Right. And you guys remember navigating's formula? Car goes by. What's the observed frequency? You remember that, right? Now I have a different poster right here. It says Doppler effect for light. And well, here could be a application. Suppose you got different galaxies in the universe. Now you could either have this purple galaxy is stationary, and the red and the blue are both moving to the left, right? Or the purple blue could be stationary, and the purple's moving to the right. I mean, all motion is relative, so they'll be identical. Right? Now, guys, one of the differences between sound and light. Let's go back to sound for a moment, because you guys are definitely familiar with this one. Can this car go faster than the speed of sound waves that it's sending out? Is that possible? Yeah, that's called supersonic. You guys remember supersonic? But can this suppose this car turns on its head beams, and now we're looking at the light. Can you ever outpace the light that you're sending out? No. So that's one reason that the Doppler effect for light looks a little different. So here's the observed frequency, or if you like the observed wavelength, it's got out in terms of that. Right? Here's the speed of light, which is like a limiting speed. And as you approach that speed, then run into all these dilation effects. There you go. Now guys, almost all the galaxies relative to Earth are what? Redshifted or blue shifted? Show of hands. Who says almost all the galaxies relative to us are a bit redshifted? Who says redshifted? Yeah. Right. Now there's at least one that's blue shifted. Do you guys know which one I'm thinking about? It's called Andromeda Galaxy. So next, I think a couple billion years, something like that, the Milky Way and the Andromeda are going to collide. And we know that because it's blue shifted head towards us. All right. Part of our galaxy cluster. I got Ian, Dallas Stars, Tommy Two-Tone, Luciana, Alexander. In some reference frame in the universe, you are traveling close to the speed of light. Yeah, true. Yeah. Okay. Now, part of what makes this tricky too is if you look at galaxies at the edge of the observable universe, well, there's a reason there's an edge because of how the universe expands, universal expansion, cosmological principle. Anything beyond that is moving definitely faster than the speed of light. The light will never reach us beyond that. Okay. But that's not because galaxies are traveling through space, but it's because space between us is expanding. It's a little different. Friend is riding on the back of a truck that is going away from you at 25 kilometers an hour. After the truck passes, your friend throws the ball at 55 kilometers an hour, but that's their own throwing speed. How fast is the ball going relative to you? So if you catch the ball, how fast is it given when you catch it? Yeah, that's another core. 30. Okay. So here, I want to draw this one out. Okay. Now, guys, this is not Einstein relativity. This is your classic Newtonian relativity. Suppose you got a big old truck right here, truck wheels, and here's your friend with the ball. Right. Now the whole truck is going forward at 25 kilometers per hour. Right. Now your friend can throw a ball at 55 kilometers per hour. Right. But that's not relative to the ground. That's not relative to like some nearby tree. Right. That's relative to the truck or to the person throwing the ball. Right. If you're over here, right, let's say you got a baseball glove, you're going to catch that ball. Right. And let's say you got a radar gun too. So here's your radar gun. Right. That radar gun reads 30 kilometers per hour because you have to subtract these two because they're opposite. Right. Okay. Now, how about this though? Guys, suppose this truck turns on its head beams, and the person riding inside the truck measures the speed of the head beams. This person outside the truck also measures the speed of the head beams. Do they both measure the same speed of light for the head beams? Yeah, that's the same. It doesn't even matter if that truck's going half the speed of light, but talked about that earlier. Right. And that would bring you to Einstein relativity. Right. That was a Newtonian question. I think that's the only Newtonian question on this whole Kahoot, though. I got Peyton, Luciana, Tommy Tucho, Dallas Stars, Alexander. The person inside a spaceship moving close to the speed of light. A meter stick held horizontally looks what? The person inside the spaceship. Yeah, just the same. Right. Remember, as long as you're in Rocket Twin's frame of reference, if you're riding along inside the rocket with Rocket Twin, nothing seems strange in your own locality. Right? Now, if you talk to Earth Twin, it's going to say it looks like your meter stick got really short. Right? Your rocket's short. But if you're inside the rocket, everything looks fine. Peyton, Tommy Tutone, Dallas Stars, Luciana, Alexander. To calculate how much rest energy an object contains, you multiply. Guys, how do you read that formula? Energy equals what? There you go. Mass times the speed of light squared. All right. It's getting that. You guys know that's the energy of nuclear reactions, right? Nuclear energy, right? Which I have a presentation for you guys at the end of today. You guys will learn about nuclear. Objects accelerated to relativistic speeds appear from Earth Twin's frame of reference to what? Only one of those is true. Not the green one. All right. Okay. So if you look at relativity equations, we'll flip over look those. You'd actually look like you were getting shorter. So the opposite of that one. You would live a longer time. You guys remember Rocket Twin stayed young and Earth Twin turned to an old man? You guys remember that? Right. But you would have more momentum than Isaac Newton would have predicted. All right, so let's look at this equation. Right. So guys, relativistic speed. Here, see if you guys are following. If you guys caught what I said earlier. Guys, if you're moving at a relativistic speed, it's supposed to be like half the speed of light. This square root, this entire square root is bounded between what and what? 0 and 1. All right, so let's throw a number at it. Let's call it 0.5. Okay. So if you take any initial time for a Rocket Twin, divide by 0.5, that takes more time. So for Earth, a lot of time has passed. And for on the rocket, hardly any time has passed at all. Here, I'm going to shuffle all the way down to the bottom here. Guys, what if the rocket length was 10 meters and you multiply by 0.5? Does that make it appear longer or shorter? It'd be shorter, right? 10 times 0.5 would be 5. Right, but this one in the middle, if you have some rest momentum and you divide by, say, 0.5, would that be even more momentum? Or here's the graph version of that equation. So Newton said your momentum is just mv. Einstein says, well, it starts off being that, or pretty close to that. But then, as you approach the speed of light, it heads off toward infinity. Isn't that? And then scientists at the Large Hadron Collider run into that all the time. You guys remember that too? Saw that. Peyton, Dallas Stars, Tommy Two-Tone, Luciana, Alexander. Standing on the ground, see a rocket ship move by 95% the speed of light. Compared to the rocket at rest, you would see the rocket's length as what? Shorter. Right. You know what? Not only shorter. Oh, well, okay. The question was, but it said 95% speed of light. Okay. Here, guys. You guys see this equation right down the bottom? Let's try it out. I'll try it. You guys try it. I want to know, what is the new length of the ship? Let's say the old length was 100 meters. You guys get that? So the rockets on Earth is 100 meters long. Earth twin, rocket twin. They're next to each other, so they obviously agree. 100 meters. I'm plugging 100 meters right here. Guys, everybody got a calculator? Everybody's got a calculator? Plug in, guys, plug in 95% speed of light. Oh, so that'd be 95% of C compared to C. It's being squared. How many of you guys have that? I'm going to punch it in this calculator off screen. You guys punch it in. I want to know what the new length of the ship is. All right, I got the answer on my screen. How about you guys? See, seriously, bunch of numbers in right here. Who's gonna get it? Who's gonna get the length of the ship? Remember the original length, let's call it 100 meters. Just throw a number at it. Let's say that V right there is 95% of C. I want to see if you guys can get this. What's the length of the ship? What's the length of that ship? Who knows how to do this? No, guys, it's that very bottom formula. That length contraction. Length contraction. Try it out.
These two.
Try it.
Okay, what do we get?
So, say the numbers again. So, let's say the rest length was 100 meters, and this V is 95% of C. So, who knows? Who knows what the length of the ship is now?
We have to. Wait a minute.
Anybody get it?
For a little bit. We didn't specify.
All right, here, guys. Here's how I type this in. So, in the place of out loud, I'll put 100. So, you guys got that? Guys, try this with me. Try this with me. Type 100, multiply by, then hit square root. Guys, see I got a square root. Make sure there's a parenthesis open. This model automatically opens the parenthesis anyway. Okay. Do 1 minus. You guys got that? Okay. Now, guys, if V is 95% of C, is that like 0.95? Right? And then the C cancels. Now, you do have to square it. So this would be 0.95 squared. This whole fraction right here is 0.95 squared. So in my calculator screen, whoops. What just happened? All right, there we go. So 100 times square root of 1 minus 0.95 squared. The answer is 31 meters. You guys see 31 meters? All right, that's the answer. Okay. Now the Kahoot question just says, is it longer or shorter? And the answer is shorter. Okay. 31 is less than 100. Tommy Tuto, Luciana, Peyton, Dallas Stars, Alexander. When an object is pushed to a relativistic speed, its momentum is measured to be. Great. than mv. Yeah. There's the answer right there. Well, here's the graph version. So remember Newton said, oh, momentum is mass times velocity. Einstein says, well, actually it's more than that, especially at relativistic speeds.
No.
Relativity equations for time length and momentum hold true for. Yeah, not only relativistic speeds, like all the calculations you guys did yesterday, but also everyday low speeds. You guys remember, I've been calling this the correspondence principle. You guys remember the correspondence principle? It says if you come up with a new theory, your new theory should be able to cover the basis of the old theory, where the old theory was fine. Right. Hey guys, let's try this. Try this. You jump in your car, you drive 995 at 70 miles an hour. Guys, what is 70 miles an hour compared to the speed of light? Is that pretty comparable, or is that almost nothing? Yeah, that's almost nothing. So with this fraction right here, be very, very, very close to zero. Right? Let's say you drive all the way to Jacksonville and back. So you're gone for a few hours. Takes you a few hours there, a few hours back. Right? Now that's from your frame of reference inside the car. What about your friend? Does your friend also agree on how much time you've been gone? I think he should. All right, let's try it out. Guess what? What's 1 minus 0? 1? What's the square root of 1? 1. So if you were gone, for, let's say 4 hours, would it just be 4 divided by 1? So so now you and your friend both agree, right? So that would be a non-relativistic speed. What I'm trying to get at is a correspondence principle. So Einstein relativity should work not just for the crazy situations like GPS satellites, but also just every day too. It has to align. If you were to travel at speeds close to the speed of light, you would notice that your none of the above. Okay. Remember, as long as you are in rocket wind's frame of reference, you notice nothing strange inside the rocket. The clock on your own rocket wall goes at beats at 1 second per second, and so on. Right. So the length of your ship doesn't change in your own frame of reference. Now call up Earth twin, it's a different story. Got Peyton, Tommy Tutone, Dallas Stars, Luciana, Alexander. If Einstein's equations for special relativity are valid, they must reduce to Newton's equations when the speed is small, give correct answers for speeds much less than the speed of light, agree with correct results of Newton's equations, all the above. All the above. Here's your correspondence principle. We've been talking about that last couple of minutes. Right, correspondence principle. There you go. Got Peyton, Tommy Tutone, Dallas Stars, Luciana, Alexander. You guys ready for the win? For the win. For the win. For the win. 10-meter long spear is thrown at a relativistic speed through a 10-meter long pipe. Now, 10 meters is when both were measured at rest. When the spear passes through the pipe, does the pipe shrink so that the spear extends at both ends? Does the spear shrink so that the pipe completely covers it? Do both shrink equally so that they're still the same length? Or any of the above depending on the motion of the observer? Yeah, any of the above. You guys remember the train going through the tunnel? Train through the tunnel? Paradox, relativity of simultaneity, the whole deal. I got this drawn out. Take a look right here. All right. So here's your spear and your pipe. When they were both at rest, say they're both 10 meters long. Okay. Now, if you are in the frame of reference of the pipe, so the pipe's not moving, and you see the spear go through at a relativistic speed, they'll make the spear shorter so the pipe covers it. But, guys, what if you hop on board the spear and riding like some scene from Dr. Strangelove? Would the spear stay its original length, but it looks like the pipe is now much shorter? Okay. There you go. There you go. All right, let's see who won Kahoot. With the bronze, Luciana, silver, Dallas Stars, and the gold, Alexander. All right, nice job. Nice job. All right, teach you guys a little bit about nuclear energy, a little history, a little bit how this works. Ooh, guys, look at that bomb right there. Bikini Atoll, 1946. So you guys know World War II ended in 1945. So think about the historical context. We have this massive military that don't super need anymore. The Cold War hasn't quite geared up. So hey, let's take this whole Navy fleet here and run out to the middle of the Pacific and explode a nuclear bomb and see what happens. I think I remember this being a lot bigger than they wave than they had anticipated, and it sunk much more ships than they thought. But there you go. And there's a lot more to that history. Well, yeah, there. So let's rewind to over 100 years ago. This guy, Ernest Rutherford, he's the guy who figured out the structure of the atom. You guys know you've learned that atoms have a positive charge nucleus and then a negative charge electron field that goes around it, right? How do we know that? We know that because that guy right there, Ernest Rutherford, was bombarding gold foil with alpha particles, if I remember right. So basically helium atoms. And most of those particles would just pass right through the gold foil, but sometimes they would sporadically bounce off at crazy random angles. And his conclusion was that the only way that would happen is if the structure of the atom was, well, what you guys probably learned in past science classes. You got a positive nucleus and a negative electron field. Right? Before that, they had this idea of like, they called it like a plum pudding model where everything was kind of mixed together. And Rutherford says, no, actually, that wouldn't be consistent with my experiment. Right? Fast forward a little time to James Chadwick. This is the guy who discovers neutrons. So if you look at the masses and the relative masses of different elements, now you guys know that on the periodic table, you can increase by an integer value, like for the number of protons. So hydrogen is element number 1, has 1 proton. Helium has 2 protons. Lithium 3, and so on. Right? But that doesn't account for all the mass. So if you also include neutrons, then that does include all the mass. And neutrons pretty close to has almost the same mass as a proton. It's slightly heavier. Now, guys, protons and neutrons, turns out, are not actually elementary particles. So there's even more to the story. Electrons are. So as far as we know, you cannot break down electrons. But protons you can break down into 2 ups and a down quark. And here, a neutron you can break down into, well, 2 downs and an up quark. Right, so, so now we have neutrons. Great, we got that. Right. Fast forward a little bit, 1930s. We got Lisa Meitner and Otto Hahn. Take these neutrons, this recently at that time discovered neutrons, and bombard a U-235 atom. So this is a particular isotope of uranium, a less stable one. And they realized, hey, you actually have this nuclear reaction. This is not a chemical reaction. This is something completely brand new. This is nuclear. And this is one of many reactions. It got krypton and barium and 3 more neutrons that could maybe spur a chain reaction. So if you have a bunch of U-235 lying around, maybe you could get a chain reaction going all at once. Okay? So they discover this, and then now the idea of having a chain reaction and gathering nuclear energy, because this process releases an enormous amount of energy. The concept is definitely there. Just how do you engineer this into something practical? So enter well, we're about to get to the Manhattan Project. You guys know we're leading up towards, right? So this pair of graphs right here, this tells the same story. Do you guys see how one graph is upside down to the other? Right. So we got one that's mass per nucleon, and there's binding energy per nucleon. And the connection is this equation down here, E equals mc squared. So whenever you run a nuclear reaction, you're actually differing the mass. If I focus on this graph on the left, mass per nucleon. Guys, what is a nucleon? What is that? That's either a what or a what? A proton or a neutron, because both of those are in the nucleus, hence nucleon. So what is the mass of a proton? What is the mass of a neutron? It actually depends on what atom you're in. And the heaviest it'll ever be is if it's inside a hydrogen. You guys see that on the far left of this right here? So here's the mass inside a hydrogen. And then jump down to helium. Here's lithium and so on. Does anybody know? I don't know if you guys can read it. It's like size 2 font. But maybe you know. Guys, what atom is all the way at the bottom of this graph? Does anybody know? It's iron. Right, so iron. So going from hydrogen to iron, you can fuse together atoms and pretty much get energy out of it during the whole process, well, except for like this jump up and a couple of those. Right? After iron, it takes more and more energy to create the larger elements. Right? So after that, if you want to say get energy out of uranium, which is one of the bigger elements, right? You want to go through a fission process and split it in half, and then that would be like this chain reaction right here. You can get energy out of it that way. Right? But if you start with iron, you can never get any kind of nuclear energy out of that. Right? Oh, by the way, guys, where do all the elements come from? So rewind about 13 point something billion years ago. There's a Big Bang, and then after the Big Bang, some millions of years pass and things kind of settle. At that point, the universe is almost all hydrogen and some helium, maybe trace amounts of other things, but it's almost all hydrogen and some helium. Right? But guys, what about in this room? Because the air that you're breathing right now is made mostly out of what? Nitrogen, right? And yeah, about 20-something% oxygen, which is good to have. It keeps us alive, right? And trace amounts of it, right? Or what are we made out of? A lot of carbon, hydrogen, oxygen. What else am I missing? Something. In trace amounts of other things, a little bit of phosphorus, a little bit, right? So where do all those elements come from? So different origins, but you can get these other elements from supernova explosion. So at the end of the life cycle of a star explodes, you get supernova. Or colliding neutron stars is another place that creates all these elements. Okay. So how about anything in our solar system? Anything in our solar system came from like some reaction that happened approximately 4.5 billion years ago. There's ways that scientists know that about 4.5 billion years ago. We get all the elements, beyond hydrogen and helium. Right? Now, the biggest element that came out of that reaction, whatever it was, supernova or colliding neutron stars, or however we got everything on Earth. Right? Do you guys know the biggest element that you see naturally in our solar system? Turns out it's uranium. It's uranium, right? Now, there are elements bigger than that, but none that were naturally achieved 4.5 billion years ago in our solar system, right? And so more on that later. Right, here's a Chicago Pile, the world's first nuclear reactor. It was built, oh, look at that, middle of World War II, part of the Manhattan Project, right? The US government is pouring massive amounts of money into developing this technology so we can get it before the Nazis get it, right? So that'd be a good thing, right? So I like to think about this history with these quadrants. So you guys know that the two halves of the nuclear story are fission and fusion, right? Fission is breaking apart large atoms like uranium. Fusion is putting together small atoms like hydrogen to make helium, right? Now you can also have an uncontrolled reaction, so basically a bomb, or a controlled reaction, think a power plant. And the first one we figured out, end of World War II, 1945, Manhattan Project, we figured out how to create a fission bomb. So there are, well, come back around to that, but let's look at this isotope of uranium right here. So you guys see this silver disk right here? So this is pure U-235. That's one particular isotope of uranium. Now, if you dig uranium out of the ground from a uranium mine, almost all of it's U-238. You guys see this pie chart here? All this blue is U-238, which is pretty stable. Can't really do too much with it. But there's a tiny sliver of this U-235 that is unstable, and you can put through a reaction, a nuclear reaction. Now, if you can up that proportion to about 3 or 4%, that's called enrichment. Now you have reactor grade uranium. You can run a nuclear power plant with that. And if you enrich that even more to 90% or more, or what he's holding right here, it's all U-235. This is highly controlled because once you have that, it's actually not very difficult to create an atomic bomb out of that. Right. Now, how do you enrich uranium? How do you go from iron ore straight out of the ground to this, what he's holding in his hands? There's different ways to do it. One way is you can gasify the uranium, put it in a centrifuge and spin it, and all the heavy stuff goes toward the outside, and all the light stuff goes toward the inside. That's one way to enrich uranium, right? And then once you have that, it's really not very difficult to create this. Here's U-235, U-235, conventional chemical explosion. So think like a gun explosion, detonator, right? And now you have a runaway chain reaction, right? Oh, so a little history too. So into World War II, we dropped a couple of bombs on Japan. The one we dropped on Hiroshima was actually entirely experimental at the time. So this was an actual uranium bomb. The one we dropped on Nagasaki a few weeks later was actually a plutonium bomb, which was the same category as we dropped in New Mexico at Trinity site to test it out to see that this would actually work. Right? But yeah, the bomb on Hiroshima was actually completely experimental. Now, what about this plutonium? It's actually element number 94. Uranium is number 92. So where did we get plutonium from? There was actually zero plutonium 100 years ago. That at least in our solar system, it didn't exist. So we had to create the plutonium. Is that Paul? Here's
Take some uranium-238, very, very plentiful. Fire some neutrons into it. It'll turn to 239. 239 is a beta decay. Beta will undergo beta decay. And when 239 does that, it'll turn into neptunium. Brand new element, not found commonly in the Earth's crust. Okay, if you find some neptunium, it must have been uranium that grabbed the neutron, yeah. And then neptunium will shoot a beta and then become. This has a longer half-life, a couple thousand years. This will last long enough so you can use it. These are very, very short-lived, very short-lived. But this stuff here, plutonium, we now have plutonium in the environment. We didn't have plutonium in the environment in any appreciable quantities before the, say, 1950s.
all right. There you go. So when we were able to finally control these fission reaction was early 1950s. So think nuclear power plants. We were able to finally do that. Okay. Do I got stuff on nuclear power plants here? Yeah. Right. So how do you extract energy from nuclear to have a controlled chain reaction and turn that into energy on the grid? Right. By the way, guys, what's running the air conditioning right now? What's running that projection right now? Approximately 20% of that is from a fission process from uranium. And here's different kinds of reactors. You guys see the most commonly used one is a high pressure reactor. There's also a high temperature reactor. You'll see later in this presentation. Look at that. So here you go. Here's your high pressure reactor. So you have some uranium, use that to boil water, create steam, turns a turbine, runs a generator. We get energy. That looks like the Rankine cycle from a few weeks ago, doesn't it? Yeah. So there's one way to do it. Right. Here's a fun tidbit. So part of the process of controlling the reaction is using what's called heavy water. So it's like water, except instead of regular hydrogen as part of the H2O, they use hydrogen with extra neutrons. It's called deuterium. And so create heavier water, slows down the neutrons enough to control this process. So that's one type of design could use heavy water, right? I think this is a little bit outdated, but the states I think is still pretty accurate. So this says about 20%. So we get about 20% of our energy on our grid from these nuclear processes. We have approximately 100 nuclear power plants just within the United States. About 100 plants it takes to create about 20% of our electricity needs. France at the top here. France gets about 3/4 of their energy needs from nuclear. So different countries prioritize differently. Right. There's nuclear reactors over time. You guys see it started in the 1950s and petered off after about 1980s. Okay. Here's a different type of design. This is not high pressure. This is high temperature. It's called molten salt reactor. You need high temperatures for that. Now, one of the advantages of this design is that it has passive safety. So if something bad happens, I don't know, workers don't show up or something goes awry for whatever reason, then do you guys see right here this freeze plug? You guys see this freeze plug? Right. So our modern day reactors, again, most of them are high pressure reactors. If something goes wrong, you end up with an explosion. It's not a nuclear explosion, but an explosion that could, like at Chernobyl, create a bunch of damage anyway, right? But with this design, if something goes awry, then it just very simply melts this freeze plug, and all your nuclear reactions just dump into these emergency tanks, and it has walkaway safety, passive safety. Yes. Okay. Now, nuclear energy. This is one of these energy sources that the advantages are kind of in the aggregate. Like how many people have died from fossil fuels? Like millions of people, because they cause like so much pollution and causing ocean acidification, the whole deal. A huge advantage of nuclear is that there are no greenhouse gases, so they're cleaner for the environment in that sense, right? The downsides are, of course, you have to figure out how to store the nuclear waste, right? It's going to be radioactive for tens of thousands of years, what we use. And also, whenever there is a disaster, of course, it makes headlines in the newspaper. So, like, that's bad too. Right? But this has some advantages, this particular design. Also, here we go. Got a sideshow for you guys. Is this video going to run? Here you go. Okay. There you go. I got to get past this ad right here. Give me Hank Green.
One thing's for sure. We humans, we need electricity now, but since fossil fuels are turning our environment into a crap circus, some scientists are telling us not to discount nuclear energy. In fact, they say that maybe we should switch our uranium-based nuclear reactors to safer, cheaper thorium-based ones. Thorium is an element, a metal that's close to uranium on the periodic table, but with 2 fewer protons. And it's named after Thor, the Norse god of thunder, which is cool. but it's not an element that we've historically paid much attention to, seeing as it's pretty much as common as dirt. In fact, until recently, most mining operations literally threw it out while they were trying to get other stuff. But a small and growing group of thorium fans say that it is the future of power production. These people are pushing the idea of adapting existing nuclear power plants to use thorium as a fuel, or just replacing them entirely with a completely new kind of reactor called liquid fluoride thorium reactors, or LFTR, which they pronounce lifter. Lifter uses a mixture of liquid salts to cool the reactor and to transfer the heat energy out of the fission chambers into something that can then power a turbine. Proponents say that such a system would be more efficient and safer than the pressurized water used to cool uranium fuel rods now, and the boiling water and steam used to transfer the energy they create. Because Lifter doesn't use water for cooling, there's no possibility of a hydrogen explosion like what happened at Fukushima. Also, although thorium is a radioactive element, it emits alpha particles, which are less biologically harmful than uranium's gamma particles. Thorium-fueled reactors use a fraction of the material necessary to run a uranium-based reactor, and they produce waste that's toxic for a shorter amount of time. 300 years compared with uranium's tens of thousands of years. And unlike uranium, it is very difficult to turn it into a weapon. So, why haven't we started building these things? Like yesterday. Well, we almost did. In the 1950s, there was essentially a competition between uranium and thorium-based systems. It was determined that uranium used in a light water reactor was the quickest, easiest way to power a nuclear submarine. And as a bonus, the waste from the process could be used to make bombs. So Washington was like, yay, uranium, while a thorium-based plant at the Oak Ridge National Laboratory in Tennessee was mothballed. Today, the biggest problem of converting to thorium reactors is expense. The reactors themselves aren't that expensive, and neither is the thorium, but the trouble is, all of America's 104 nuclear power plants currently run on uranium, and a lot of people doubt whether going through the expense to retrofit the existing plants would be worth it, since they would still produce radioactive waste, just not as much. In the meantime, you will be unsurprised to find that China is taking the lead on developing Lifter. So I guess maybe we should just see how that goes for them. What do you think? Thank you for watching this episode.
All right, yeah, so there are proponents of thorium over uranium, so here's a couple of points. Thorium is a lot more abundant than uranium, 3 times more. If you look at the nuclear waste that comes out of the thorium process, it's hardly anything at all. It's like less than 1%. And also those waste products are not radioactive for nearly as much time. So hundreds of years rather than tens of thousands of years. It employs that molten salt reactor I was showing you guys a couple slides back. So that has passive safety. And can't create nuclear weapons from it. So there's some proponent points. All right, so a lot of last slides have been the right side of either of those graphs, where we're splitting apart large atoms like uranium or thorium to get energy, that extract energy. But you guys see a much larger jump going from hydrogen to helium. Right? Now that jump is hundreds of times bigger, almost 1,000 times bigger. I might just call it 1,000 times as much. You get 1,000 times the energy from fusion that you get from fission. Okay? So fusion. Now, have we created a fusion bomb? Yeah, back in the 1950s. So first in the States and then shortly after the Soviet Union. Now, a hydrogen bomb, which again, about 1,000 times as powerful as what we dropped on Hiroshima and Nagasaki in World War II. Also called a thermonuclear bomb. That's never actually been used in war, but we have them. So, well, I guess modern day Russia has them, right? Got those. And so this is the energy of the power stars, starlight, and sun. This is hydrogen and helium for the most part. That's what that process looks like. Okay, and there you go. Here's how you create a hydrogen bomb. Right. Right. So it looks like. Right. Now, can we ever control a reaction? That's to say, create a power plant from this. Not right now as of today, but there's this joke in science that fusion reactor processes are always 20 years away. Fusion power plants are always 20 years away. So yeah, hopefully within our lifetimes, because this would be a really, really good technology to have. Here's Lawrence Livermore Laboratory right outside San Francisco. They're using lasers to try to achieve fusion. Here's a couple of guys you can say working here for scale. You can see there's if you ever see this looking chamber, it's a little bit different process of trying to achieve fusion. So yeah, so hopefully soon have a fusion process. Bring a little science article there. All right. All right, so that's going to be a wrap on today.